my role in our project was the role of FPGA designer. Our goals with respect to the FPGA component were to implement a TinyOS compatible, platform compatible sensor node, typical of the Mica 2 type sensor nodes. Mica 2 sensor nodes use TinyOS platform and typically have either an MSP 430 microcontroller or an Atmega 128 microcontroller. So FPGA development started with selection of a proper FPGA core. The selection criteria for the FPGA core were to have the smallest area FPGA device, having low power consumption and low cost, yet still be suitable as a replacement for an AVR device microcontroller. So accordingly, we obtained open source cores for the microcontroller substitutes to be test compiled to various FPGA family devices. No open source core was found to correspond with an MSP 430 device. However, a handful were available corresponding to that Atmega 128 device. One specific open source core, PAVR, was obtained from opencores.net and test compiled to various Actel Igloo family FPGA devices. We found that the PAVR core would potentially be synthesizable to an Actel Igloo Nano 250,000 gate device, and we obtained the Igloo Nano 250,000 gate device in the form of an evaluation kit, which was shown in the hardware part. The development of the PAVR core then began, which revealed several deficiencies in the open source PAVR core. Specifically, the instruction set was incomplete with respect to features of the traditional Atmega 128 controller. Most of the input-output ports were missing from the open source PAVR core, and more importantly, critical controller functions such as UART and SPI were also entirely absent from the open source PAVR core. I then attempted to further develop the PAVR core to include these features. However, final synthesis of the fully developed core indicated that it would actually need over 150% of the available logic cells of our Actel Igloo FPGA. And this is a synthesis report showing the excessive requirement of the core cells using our Actel Igloo device. Relatedly, we obtained an alternative open source for the AVR core, and to be used at this stage. Initial analysis of the AVR core, open source core, indicated that it would use approximately 80% of our Igloo Nano slices. However, developing the core ran into some additional difficulties with the AVR core, in that it was specifically written to target Xilinx family devices, Xilinx brand devices, and it relied heavily on Xilinx libraries, intellectual property, and inferred block RAMs. So I eliminated some components of the AVR core that were unnecessary for our project, such as JTAG, which wasn't used in our project. And then I attempted to reconfigure the core using Actel brand intellectual property and libraries, and to infer Actel RAM instead. However, the AVR core reconfigured has yet to synthesize properly. As a last-ditch effort, we we attempted to synthesize and implement the AVR core on a Spartan 3 device, which it was designed for. Specifically, I attempted to implement the AVR core on the Spartan 3 100,000 gate device on the Basis 2 board that we had on hand from EC 448. However, logic utilization of the AVR core on the 100,000K Spartan 3 device was, again, over the number of slices available. Accordingly, we have yet to realize a core that we've yet to realize an FPGA core that works properly and is within the size requirements of our project. Final analysis of the fully developed PAVR core and AVR core, Xilinx specific, indicates that PAVR would potentially be implementable on a 500,000 gate or higher Actel board, and that AVR core, the Xilinx specific core, would potentially be implementable on the Spartan 3 XCS 1200E device. However, these devices are considerably more expensive than our own, than the device that we selected, costing roughly $50 to $80 compared to $10 for the FPGA core that we had targeted. And now Chan is going to discuss the administrative aspects of our project, including lessons learned.
I will talk about the code analysis and lesson learned. For the part cost, we spent about $965. Include major components, the CC1000 kit, FPGA RAM, FPGA starter kit, CC1000 ADC. So we have to study with the PCB after software. So we have to spend about verification, assembly, and testing sequence with the PC board. The labor cost, here is our contribution about it, and labor cost is the 19,180, and total of the development is 20,145. We estimate the production cost is about like $100. Include part cost, PC board, labor for salary, shipping, and handling. Lesson learned for the PCB layout, we have got the experience with the PCB layout, how to deal with the socket mount port. We ensure code complete before synthesize, and usually for open source code. And our team should check that like if the project rely on the open source code, we should use the Xilinx device than the Actel device, because most of the open code designed for the Xilinx design. Should be integrate early to use, have extra hardware, verify everything, should be like double, triple check the design. I would like to thank to the Dr. Kat, first guidance from faculty advisor. Thank to Professor Michael Young for feedback for the PVC layout. Thank to Avi Rami, thank to John Pham, and any questions?